in doing projects on quantum computation and organizing this kind of workshops in quantum chemistry, quantum materials, and quantum computation algorithm like that. And Calcutta itself is host to a lot of institutes like ISI Calcutta, which has been very active in this area, particularly foundations of quantum mechanics, quantum computation, and things like that. Now, as Professor Nori might have heard, Government of India has started this NMQT, National Mission for Quantum Technology, which came after Quantum Enabled Science and Technology project for the last 3 years. And this Quest project is coming to an end, and NMQT has started with 5 areas of emphasis: quantum communication, quantum computing, quantum materials, and imaging and sensing. And you can see, it's remarkable to see Professor Nori has significantly contributed to almost all these areas. So it is a great opportunity to hear from him. And students, please take it easy. They have your notes. As Professor Nori pointed out, many of the speakers will give you access to their materials and already prepared things in their website. So, this is an opportunity to ask questions, to learn. And so I will not take much time. I am myself curious to hear Professor Nori. So please proceed, and we are here. Thank you once again for joining with us.
Yeah, thank you, Professor Panikbhai. So today's first plenary talk will be by Professor Franco Nori, and let me give a brief details of Professor Franco Nori. And Professor Nori is a well-known name in the arena of quantum computation. He is currently associated with Theoretical Quantum Physics Laboratory and Quantum Computing Center, RIKEN, Japan, and also he is associated at the University of Michigan, USA. His research is primarily quantum computation and quantum information processing. He has done research in computational physics, transport phenomena, light-matter interaction, as well as the dynamics of complex systems. His research work is interdisciplinary and also explores the interface between atomic physics, quantum optics, nanoscience, and computing, etc. His research group actively participates, particularly emphasis on the superconducting Josephson junction qubits, scalable quantum circuitry, and improved designs for their quantum control. An underlying theme of his work is to better understand nanoscale quantum systems and devise methods to control them. His research group uses physical models to make predictions that can be tested experimentally and that can be used to better understand the observed phenomena. And let me inform few things that he is also a fellow of the American Physical Society and Optical Society of America and UK's Institute of Physics and American Association for the Advancement of Science. In 2014, he received the Maxo Foundation Award, and in 2013, the Prize for Science and Technology by Ministry of Education, Culture, Sports, and Science and Technology of Japan. So with this brief introduction, I invite Professor Franco Nori to deliver his talk, and his title of the talk will be Quantum Optics with Giant Atoms, Decoherence-Free Interaction between Giant Atoms in Waveguide Quantum Electrodynamics. Professor Nori.
Oh, thank you for the kind introduction. Can I share the screen, because it says that?
Yes. So,
okay, so therefore here.
Yeah.
So let me see. Do you see the screen now?
Yeah. No. You have to maximize your slide. Yeah. It's coming. Yeah. Now we can see.
Now?
Yeah.
See it?
Yeah.
Okay, good. So let me see if I can move this here. Oh, thank you very much for the kind introduction. Welcome, everybody. I'll be talking about giant atoms, a new frontier in quantum optics. And as you can see here, in the first slide, there is a schematic diagram of a blue atom and a red atom interacting with each other. But the red atom is going to be replaced by a red giant atom made on a chip. It's a superconducting qubit here. Can you see my pointer?
Yes.
The arrow. Okay. So as you can see here, this red a qubit here is interacting with the blue one, but not via this schematic way as shown here, but via these different coplanar waveguides. The coplanar waveguides, they are a 1D electromagnetic environment that allows one atom A, the red one, to interact with the atom blue in one side, then the blue one interact with the red one on the other side, and then with the blues on the other side. So therefore, the atoms can talk to each other via these channels, via these waveguides, where electromagnetic with photons can propagate longitudinally. So this is, let me see if I can get the screen here. So this will be a talk about quantum optics using giant atoms. Let me start with a haiku, which is a short Japanese poem of 3 lines. Superconducting circuits with Josephson junction qubits can behave like artificial atoms on a chip. So that's with this short poem. I'm going to start this talk here. These superconducting circuits, as we have seen on the first slide, can simulate or emulate atoms. So they can act as a quantum simulators. If the students in the audience would like to see a brief overview on quantum simulators, there is a short one with no equations and color pictures, like a Scientific American overview. It was published in Science a few years ago, and the main ideas are there. If you wish to see a longer one, a much longer review, that is in Reviews of Modern Physics, is more recent one also. And all of these are available on our website. So therefore you can access them from anywhere, from your home, from a coffee shop. And these are all pedagogical, and there are also pedagogical broad overviews related to quantum information, like this one here, Quantum Technologies, a new story. This is like 2 pages long, Physics World, Natural and Artificial Atoms for Quantum Computation. That's overview mostly of the experimental aspects of the subject, and some pedagogical overviews on superconducting circuits and quantum information, atomic physics, quantum optics, superconducting qubits. These are all Physics Today, Nature. They've been translated into different languages, especially Physics Today has been translated to quite a few languages. And they're all pedagogical, simple, very few equations. So if you wish to read more, there is a comprehensive, over 100 pages long review on microwave photonics, use superconducting qubits. These are all available on our website. You can just click the PDF, the link to the journal or the archive, but the PDF is the published version. And a very pedagogical overview with Anton Fries-Kokum on quantum bits and Josephson junction in this book, but the chapter is free of access. Even in the actual book, essentially, I paid extra money to make this. Is the only chapter which is available for free. Open. The other chapters are not open access there, but ours are all available to all, are open access. So these are pedagogical overviews that for students who would like to see this field in more detail are available in those reviews. So brief summary of the talk. In quantum optics, atoms are usually approximated as point-like compared to what? Compared to the wavelength of the light they interact with. However, recent advances in experiments with artificial atoms built from superconducting circuits have shown that this assumption can be violated. And the reference for these are here. Essentially, Gustafsson et al. In Science. The work started in Chalmers in Sweden by Anton Fries-Kokum, Göran Johansson, Per Delsin, and collaborators. Gustafsson, they did great work. And then afterwards, our group and other groups follow up this pioneering work. In fact, some of the pioneering work in Anton, he joined our group for about 4 years, and we continue working here on this. So these artificial atoms can couple to an electromagnetic field in a waveguide at multiple points, which are spaced several or many wavelength distances apart. These systems are called giant atoms. They're attracting increasing interest in the past few years. There's an excellent review by a leader in this field, which is Anton Fries-Kokum, who was Chalmers, began the work, and then joined my group for about 4 years. Now he's back to Chalmers, they're permanent. The key point is that there are interference effects due to the multiple coupled points. So you can imagine this atom like having many arms, and these many arms are touching the environment, which is this 1D electromagnetic waveguide that can meander around. And then depending on where the arms are located, you get different interference effects. And then these atoms are interacting with each other to the waveguide without losing energy into the waveguide, which is remarkable. And then I will briefly review some of these developments. And then we have also recently shown that a giant atom can couple to waveguide that can give rise to chiral bound states. So, therefore, eventually we'll be talking about the paper, this one here in Physical Letter 2018, and then the experiment was done 2020 at MIT, was published in Nature. And this area is still further development. The main message has already been summarized. Why? Because most people fall asleep after the first few slides. This is a typical conference where most people, they just fall asleep. But before you fall asleep, I wanted to give you the overview. So I'm going to start first an introduction, atom sizes and their history. Then one giant atom, how to do frequency-dependent relaxation rates. Then multiple giant atoms, how to get them to talk to each other in a decoherent-free way, which is important. You want atoms to interact, to do gates, but you don't want it to decohere, at least not too fast. And then at the end, if there is time where people ask in the question period, might be talking about chiral quantum optics and giant atom, which we're still working on this now. And then a summary outlook. So let's start with the introduction. Atom sizes and their history. So the interaction of light and matter has been studied for quite some time. And then important papers were obtained in the 70s, 80s, 90s by Serge Haroche, Jean-Michel Raymond, Michel Brun, and others. And Serge Haroche got the Nobel Prize about a decade ago on this light-matter interaction. So is everything being solved, or there are new directions of research? The problem initially is that the dipole coupling, the dipole moment of atom is very small. It's charge times distance. So therefore, superconducting circuits created a revolution on light matter interaction and cavity QD because the atoms could become larger. So you could have more charges and you could have longer distance. You could have like the analog of an antenna, much bigger antenna. Many things have been done, but people thought, well, we already achieved strong coupling, ultra strong coupling. So what else can be done in this field? So let's look at small atom. The size of an atom is usually small compared to what? Compared to the wavelength of the light it interacts with. So wavelength is much larger than the atom. The dipole approximation assumes the atom is a point, neglecting spatial variation in the electromagnetic field. Now, if you look at atoms in optical light, or Rydberg atoms with microwaves, or quantum dots in photonic crystal waveguides, or superconducting qubits interacting with microwaves, in all of them, you will see that the ratio of the atom size to the wavelength of the light is very small. How small? So the typical atom is about 10 to the minus, atoms are typically 10 to the minus 10 meters, and then the wavelengths are between 10 to the minus 6 to the minus 7. So the ratio is 1 part in 10 to the 3, 10 to the 4. So the atoms are very small compared to the optical light, about 10 to the 3, 10 to the minus 4. It's very. Rydberg atoms are also small, and people say, wait a moment. People say it cannot be possible because Rydberg atoms are supposed to be large. Large compared to what? They are large compared to normal atoms, which are like, instead of 10 to the minus 10, you have 10 to the minus 8, 10 to the minus 7. So yes, they are large compared to normal atom, but they are small compared to microwaves, because microwaves are about a centimeter wavelength. So you take the ratio of the atom, Rydberg atom, compared to the wavelength of microwaves, you get 10 to the minus 4, 10 to the minus 7. So therefore, the Rydberg atoms are extremely small. And this is what Haroche, Jean-Michel Raymond, and Michel Brun and others were doing for a while. That was in the Nobel Lecture 2013, and there was work, yes, the Nobel Prize about a decade ago or so on this. It's a great work, but these are small atoms. You can also look at quantum dots in photonic crystal waveguides, and again, the ratio is 10 to the minus 2, so the atoms are still small. If you look at superconducting qubits interacting with microwaves, the ratio can vary to 10 to the minus 4, which is small, to 1, which is comparable. I mean, this is, now we're talking about the small atoms are getting bigger and bigger. So this is an overview of how light interacts with matter using atoms, Rydberg atoms, quantum dots, superconducting qubits, and they're all small compared to the wavelength of the electromagnetic radiation. Now, in the giant atoms is coupling to electromagnetic field at multiple points, which can be wavelengths apart. So imagine to be an atom that has many arms, and these arms can touch the environment at far away locations. So what can you do with this? So let's recall, this is like elementary physics, quantum harmonic oscillator. They're equally spaced energy levels. So you have your LC circuit, and your LC circuit, you get these equally spaced energy levels. And this is not good for control, because if you put the microwaves, you're exciting 0, 1, 1, 2, 2, 3. You're not distinguishing any of them. You're not selecting them. So you replace the inductor by a nonlinear inductor, and that's the key idea, to go from LC circuit, which is an oscillator, to a nonlinear oscillator, because then the energy spacings are not equal. So therefore, the Josephson junction is a nonlinear inductor that allows you to actually target the 0-1 transition, or the 1-2 transition, or the 2-3. So it allows you control, allows you the possibility of manipulating the circuit in ways that you cannot do it in a harmonic oscillator. So therefore, the LC oscillators are made anharmonic by the nonlinearity of the Josephson junction, which is a sandwich, like aluminum, aluminum oxide, aluminum. So you have a nonlinear inductor. Good. So now this is standard superconducting qubits. The first giant atom was done in Sweden, Chalmers. They were coupling a superconducting qubit to surface acoustic waves through an interdigitated transducer, IDT. So therefore, let me just, so this is the circuit here. When you magnify this here, you get this picture here, which is about 5 microns. When you magnify this here, you get this this capacitor, which is interdigitated. It's like having the two hands passing past each other like this. So the capacitor has more ability to store electrical charges there. But in this case, the ratio of the atom to the wavelength is 1 to 100. So therefore, you can have in this kind of systems, atoms which are huge, which are up to 100 times the wavelength they're interacting with. But they're interacting here to surface acoustic waves. So therefore, this is a coupling superconducting qubit, which is shown here, the surface acoustic wave through this interdigitated transducer. Sorry, this is now you can see this better. Sorry, before it was very hard to see. You magnify here, 5 micron, magnify here. You can see this interdigitated transducer, which can be magnified here even better. So you have here the two Josephson junctions here. This is squid, and this is the interdigitated capacitor generating sound, which is detected here by this acting like a microphone. So you can imagine here the atom talking, but we cannot hear the atoms talk. We need to have a special microphone, and this is the microphone to catch the quantum of the sound wave. So this superconducting qubit, which is built to listen as well to see. Most qubits can see, but they cannot see in the visible. They can see in the microwave regime. So they react to microwave photons, but they cannot listen. This one, they can actually listen. They can actually talk. They can emit sound. They can be, so they cannot touch. They cannot feel. You cannot talk to them yet, but that might be changing in the future. So therefore, in the future, there will be more experiments where quantized sound-matter interactions will be probed instead of the usual quantum light-matter interaction that people have been studying for the past 40 or 50 years. So the light-matter couplings will be transformed or will be studied into sound-matter couplings. We'll have cavity quantum phonon dynamics instead of cavity quantum electrodynamics. So, and this is what's happening here. So this is generating the sound, propagates, and then it can be detected with a microphone. Let's look at the classical and quantum sound. In A, this is from this Roscoe and Tahan in Science. This is a summary of experiments done by the Chalmers group. The ultrasound imaging works by creating and detecting sound wave with piezoelectric crystals. You have a handheld wand. B is the schematic of the superconducting device of the group in Chalmers that operates in the quantum regime at cryogenic temperatures. An acoustic transducer coupled to a superconducting qubit is fabricated on a piezoelectric substrate. The surface acoustic waves are shown to interact in a quantum wave with the artificial atom. So therefore, the qubit coupled with a surface acoustic wave, which can propagate on this gallium arsenide piezoelectric crystal. The strain and the electric fields are directly coupled, and they produce a natural interaction mechanism for superconducting qubits. So therefore, these surface acoustic waves transducer are integrated to the qubit, which can act like a speaker, can talk, and can act like a microphone, can actually, like an ear, can listen to it. So this is this one here, the interdigitated transducer, which is the analogs of the one shown in A, can generate the surface acoustic waves directed toward the sound sensitive qubit, because the qubit can be excited by sound or can be excited by photons. Exactly. So therefore, this interdigitated transducer can detect acoustic waves that reflect back from or are generated by the sound sensitive qubit, which one might call it a sound qubit. So therefore, this transducer is like what I'm using now. I'm using a microphone here on the, actually I have two transducers. I'm using one here on the microphone to talk and one here on my ears, changing electrical signal into vibration. So this is the same. They're all transducers. So, and this is translated or transduced the incoming sound wave to an electrical signal that can act as an input signal for the qubit. So therefore, they can interact with phonons of the same frequency as those produced by this transducer. So the qubit can be used to probe the quantum nature of sound because the energy levels are not equally spaced. So therefore, they are like essentially acting like a qubit for light and a qubit for sound. So the phonon or quanta that make up the sound wave can be absorbed by the qubit, which starts at the ground state at low temperatures. And then when it is in resonance, a phonon can be absorbed as a whole, and the qubit is excited from the ground state to the first excited state. A subsequently impinging second phonon cannot scatter until the first phonon is released, because it does not match the splitting between the first and the second excited state. So the experiment showed by continuously changing the rate of impinging phonons from a much lower to much higher rate, then you can actually reach the resonant condition where the sound quanta are actually absorbed. The artificial atom reflected sound on resonance and did not for non-resonant condition in a manner similar to the one seen for circuit QED. Also, they did micro-radiation, independently excite and radio qubit without sound, and you can excited atom can emit a phonon. So you can excite it via light and it can decay via sound. So therefore, it is possible to excite them either way. When the sound wave is detected after a while, because it takes about 14 nanoseconds to propagate, the delay corresponds to sound propagation time. So actually you can realize that the sound detected originated from the qubit located 14 nanoseconds time away from it. Further experiments that use both acoustic and microwave drives on the qubit show additional analogs of atomic physics, specifically the outlet-down splitting related to the Stark effect and other effects. So therefore, as you can see, this system, you can actually replace the study of light matter coupling by sound matter couplings and start studying cavity quantum phonon dynamics. Now, this is an example here of this giant atom. It's called X-Mon Island connected to a squid, which is two Josephson junctions where the magnetic field can change. There's a ground plane here. Transmission line is the environment. The way the atom talks to the world is via this transmission line, is the environment, and it's happening at certain points. So the atom has many arms. The coplanar waveguide confines microwaves to the chip, creating a 1D electromagnetic environment. It has, coplanar waveguide has a center conductor and two ground planes, like a cross-section of a coaxial cable. You take a coaxial cable, you slice it, and that's what's in the middle. So that's the transmission line. The squid is a junction and a junction here, superconductor here. So it's like aluminum, oxide, aluminum, the current is split here. And this behaves like a flux tunable inductor or nonlinear inductor. And squid refers to superconducting quantum interference device. So it's SQUID. It is not this type of squid. Sometimes students are confused. Why there are squids? Do they have lobsters? Do they have oysters? Do they have octopus? No, it is not this kind of squid here, but it's this kind of squid here, which is this one here. This is explained beautifully in Feynman Lectures Volume 3 when he's talking about interference in quantum mechanics. So the basics of squids, you can find it in a textbook like Feynman Lectures Volume 3, beautifully explained. So that's what we mean by a squid here. So therefore, now let's talk about, okay, this is an overview of the experiment done at MIT where these two qubits here are connected to one arm here and then touch the second qubit in this arm here on the one side and then touch it on the right side here, on the right side here, and then out. And as you can see here, the qubits are shown in yellow. the readout in red, so it's gravity information, the control, the flux lines are in green, and the waveguide, which allows them to talk to each other, in blue. So this part here, about 200 microns, typical length scale, is a magnification of this here, and this is about 1 millimeter. And this is in a chip here, and the red is magnified here. So this is like this is about 50 microns here. So the system is pumped in from the left and the photons come out to the right. The work was started at Chalmers by Anton, Fritz Kokum, Per Delsin, George Johansson, their groups, and then Anton joined my group for about 4 years. And then we're working here with a group at Oxford, Peter Leak, MIT, Will Oliver and collaborators, and other postdocs in the group, plus other people listed below. It's a collective effort of many people in different places. Now, let's look at one giant atom, frequency-dependent relaxation rate. And then you can have either the standard situation where there is 1 qubit coupled at a single point in a waveguide, which is the environment, or you could have the atoms coupled at 4. It could be 2, 3, 4, 5, and multiple points. And you can actually decide where the coupling is. So you have control over the X1, X2, X3, X4. So therefore, you're controlling interaction with the waveguide modes, because here, as you can see here, the atom goes from 0 to 1 and 1 to 0. Hold on for a second. There's some noise out there. Sorry. So therefore, 0, 1, 1, 2, you can actually decide the location, X, of the coupling, and also the coupling strength. You can make the coupling strength weak, strong, or large. So therefore, you can actually sculpt and control interaction with the waveguide modes. And there are additional time scales you're including when there is travel across the atom from X1 to Xn, or X1 to X2, etc. So therefore, when you control the location of the atoms and the coupling, you're actually controlling the relaxation rates. So you can mimic the structured environment. This is called reservoir engineering. You can design some atomic transitions to couple strongly, while all the transitions couple weakly to the environment. Like in this case, you can put equal coupling strength, equal spacings between connection points, or here there are 4 connection points. So you can have a design with a wide minima, like the red curve here. So at this X2 minus X1, you can have a parameter regime where the relaxation rates are essentially 0 in a wide range, or a wide maxima, blue curve here in a different range, or multiple maxima in the black curve. It could be maximum here or here, or minimum here or here. So therefore, you can design, you can mimic the structured environment. You can actually sculpt the way you're interacting with the environment. Now we have multiple atoms. You can actually control the way they talk to each other. And this is important. When I do 2 qubit gates, you wanted to have low decoherence, or ideally decoherence-free. So therefore, let's have these 2 qubits talking to each other, either in an open waveguide, photon comes here, or closed, where the photon comes here, bounces here, and then gets out. The contact points will be X1 and X2 because they're here 2 qubits. And then, but then if you have 2 giant atoms connected at multiple points, then you can have a separate arrangement like AABB, because the connections are from atom A, atom A, atom B, so ABB, or braided arrangement, ABAB, ABAB, or nested arrangement, which is ABBA, which is a very suitable name for since most of the work started in Sweden. So you have A, B, B, A. This will be the nested arrangement. These are described in detail by this work, which is available on our website also for open access. So we studied setups where multiple giant atoms are coupled at multiple points to when the waveguide, and we showed that the giant atom can be protected from the coherence to the waveguide, but still have exchange interactions mediated by the waveguide. They can still talk to each other, but there is no decoherence, which is very unusual. I mean, this is different than decoherence-free subspaces because the entire multi-atom Hilbert space 2 to the n states for n atoms is protected from decoherence. This is not possible with small atoms. So the system allows you to do things which are impossible with the normal atoms. We further show that this decoherence-free interaction can be designed and set up with multiple atoms to implement, for example, a 1D chain of atoms with near neighbor coupling, or a collection of atoms with all-to-all connectivity, where every qubit is connected to every other qubit. This has been implemented experimentally, but not with giant atoms. Has been implemented with the other ones, but the experiments with all-to-all are coming in the future. How do you describe this theoretically? So you write a master equation. So you write the density matrix evolves in time. You look at the two-level system for atom A, qubit B is a two-level system, so sigma Z for A, sigma Z for B. They're talking to each other. So therefore, if B loses an excitation, A is excited. Or if B is excited, then A loses an excitation. So this exchange interaction between A and B. But there is also the individual relaxation terms involving the density matrix, and the operator sigma A minus is the decay for decay gamma A for atom A and gamma B for atom B. But also there is the collective relaxation involving both of them. The master equation has quite a few terms, and you need to take into account all of them because the system here is an open quantum system. You need to take into account the entire master equation. To do this properly can be a bit tricky, but there is a powerful tool called QTIP developed in our group that allows you to do these things in a straightforward, user-friendly manner and represent the results beautifully with different kinds of plots. When the distance x1 minus x2, which is proportional to a phase, gives you a phase corresponding to 2 pi, there is no exchange interaction. So there is a maximum collective decay. We call it subradian state. When phi changes, because the distance between them, it becomes different, becomes pi over 2, then you have maximal exchange interaction, but there is no collective decay, but the individual decay remains. This is a bright state. So it's very difficult to find a place where all the good aspects are maximized and the undesirable aspects minimized. So we start looking at a catalog of many different possibilities for open resonators, closed resonators, different kind of combinations to see which one will provide you more benefits and with less downsides. So here the frequency shifts exchange interaction between qubit A and qubit B, the individual decay of each, the collective decay. So therefore, this is for small atoms here, for small atoms and a mirror, because it's terminated at the end, it's a closed resonator. Separate giant atoms, braided giant atoms, nested giant atoms, and then we can have the results analytically. So let's plot them here because it's easier to see the results when they're plotted here. Once you plot them here, you see, if you focus, there are many, many plots here, but let's focus on the green ones, which is AB, AB. The coupling G is the green line, is very strong, it's above 1 throughout most of the this phi. So you can actually move x1 and x2 far away from each other or close to each other. It doesn't matter. The coupling remains above 1 or above 1 for a very wide range. So this is remarkably good. The individual decays became near 0 around pi/2. So this is the best spot for you to work if you want to do. But also the collective decay goes to 0 around that point. So you can have a place where you can have a strong enough coupling, which is what you want, but then 0 individual decay and 0 collective decay. So therefore, among all these possibilities, this one here, D, is the one that checks all the boxes, because requires like many of these issues with quantum computing. You need to check many different possibilities and see which one works the best, and is that one there. So the braided setup D is the only one that enables completely protected interaction. You can have non-zero coupling, but the individual relaxation rates are 0. That means decoherence-free interaction. Because the individual relaxation rate 0 implies that the phase acquired traveling between the connecting points is an odd multiple of pi for some integer, n. The collective decay is set by the interference between emission from connection points belonging to different atoms. So the collective decay involves the connection of different atoms, and the individual relaxation rates the connection within an atom. But the sum of this contribution will be 0 when the emission from 2 connection points of one atom interferes destructively. So once you have all these things put together nicely, then you can have all the, in the case of giant atom, the 2 inner connection points are placed in between the 2 connection points of the other atom. The contribution of the 2 connection points of the other atom, they don't need to interfere destructively. Anyhow, at the end, you can have arbitrary bare relaxation rates for each connection points, arbitrary distances, but still negligible travel time between connecting points. So therefore, the results here are robust over a variety of different knobs you can vary. And this is the diagram number 1, where you can get here. In this case, you connect to point X1 of atom A, then X1 of atom B, then X2 of atom A, and X2 of atom B. In this case, with X1 of atom A, then here X1 of atom B, then X2 of atom A, and X2 of atom B. So this is the schematic diagram of what's shown in the background there. So the summary so far is that these giant atoms are coupled to multiple points separated by several or many wavelengths. The multiple coupled points allow you to control interference effects, and you can design this frequency relaxation rates for a single giant atom. But when you have 2 braided ones, you can completely decouple the entire Hilbert space, not just a single dark state from the waveguide. So there's no decay, but still have a strong exchange interaction mediated by the waveguide. This is remarkable, and this is not possible with giant atoms. So let's see, how can this be tested experimentally? So we see here there is a long meandering transmission line in blue, creates a multiple wavelength distance between the qubit. This is done by Cannon et al. In the group at MIT in collaboration with us, but this is a remarkable experimental feat that they managed to achieve. And this is a magnified view of the qubit here, which is measured in red. This is the red readout. Green is the flux line for the control. Yellow is the qubit, and blue is the waveguide that allows essentially the photon to interact with one, and then with the second qubit, and then with the first qubit on the other side, and the second qubit on the other side, and get out. And all of this is a detail from here. And so you can see these, like if a photon is coming here, it's moving in this direction, then here, then here, then here, and then out. So the readout is in red here, and the control lines are in green. Frequency-dependent relaxation rate. So there are tunable coupling for a single giant atom. T1 traces are shown there and fits for qubit A for 3 different qubit frequencies. And then the fitted T1s are the ones here, which is like from 3.1 microseconds to 31.5 microseconds. So about an order of magnitude increase here when you go from here to here. And this corresponds to essentially moving and this decoherence-free subspace point here. So therefore, when you have the measured relaxation rate, which is 1 over T1 for qubit A as a function of frequency with the fit of the theory solid line. So the 3 green arrows correspond to relaxation rate for the T1 traces shown in A. So the qubit decouples from the waveguide at the decoherence-free frequency, which is around here, with a certain lifetime, which is about 31.5 microseconds. So you excite the system, you wait 31 or 32 microseconds, and on average, it's going to decay to the ground state. But this happens when you are at this point here. So you need to excite at this qubit frequency. So you're exciting 1 qubit and you're monitoring through the readout resonator, and you change the relaxation rate by more than 1 order of magnitude. This can be seen also looking at these expressions linking the delta X between the coupling points and the phase between them and the relaxation rate. If you couple 2 of them together, then there is a measure exchange interaction here, G, because now you have the decoherence-free frequencies, 4.6 something here. And then the fit to theory solid line is plotted with the data red dots, and the coherence-free frequency shown is the dashed vertical line. The qubit spectroscopy for an avoided level crossing central decoherence-free energy is shown right there. The frequency of the applied drive is swept to probe the qubit frequencies for multiple qubit detunings. Therefore, you're sweeping the qubit detunings here and see how the system responds. And then, even though the qubits are decoupled from spontaneous emission into the waveguide, the qubit exchange interaction is mediated by virtual photons in the waveguide is measured. So this essentially this 2 megahertz coupling. So these energy levels are actually exchanging energy with each other. There is exchange of virtual photons in the waveguide. And so therefore here what's been done is to tune both qubit frequencies into synchrony to find interaction strength or resonance, and the non-zero interaction at the frequency protected relaxation rate can be measured. So this is an overview of how, instead of looking at small atoms coupled at one point, we consider to have coupling at 2 different points, and then even better to put 2 of them braided together in this way. By braiding them like this, then it's possible to have them talking to each other without losing decoherence, without losing coherence. So this schematic diagram has been implemented following this diagram here into this chip here. This is the MIT chip here. And the magnified version of this rectangle here is shown on the left here. Now, they also did the design with 3 coupling qubits. So therefore, there is here, you can have them on equal coupling strengths and spaces. You can actually decide where to do this connection. So the atom is like multiple arms touching the environment at X1, X2, X3, but then you can touch it on the left side, A, on the right side, B. So it's atom A is here, atom B is here. So this is the coupling X1, X2, X3 on both atoms. So the photon comes here, talks to one atom, then the second atom, then goes here, then it goes back here, and then it goes here, and then goes here, and then it's out. So he's talking to the atom on the left side, on the top, and on the right. And here the coupling is small because, I mean, it's short, and here the coupling is stronger because it's long. So you can decide at one point X in the waveguide you're connecting, but also the strength by having a wider, longer exposure. So it could be, or a shorter one. They measure and fit the single qubit relaxation rates, and then so in this case, it is possible to design in a way that the coherent free subspace is, let's say, around 4.5 and 5.2. The coupling strength inferred for the fits are obtained. And then, so this is the measure and fit the single qubit relaxation rates are in blue, which is 0, 0 for qubit 1 and qubit 2, and the exchange direction strength between them in red. So these are omega DF1, omega DF2 are two frequencies in which the qubits are protected for relaxation, but this enables turning protected interaction on and off by detuning the qubits. So therefore, you can start by exciting with a pi pulse qubit 2, and then have them interact with qubit A for, let's say, a period of time, 170 nanoseconds. Then afterwards, detune them here, and then read out. So they're off resonance, in resonance, talking to each other, and then off resonance. Then it is possible to do the square root of the I swap gate, preparing the state 0, 1 minus I0 with 94% fidelity. Is the first experiment on this. Eventually, this could be improved. And this provides a universal gate set. So the excitation of the yellow and the purple keep excited. So you're exciting qubit A, but then B is asleep, then qubit A goes asleep, qubit A is awake, and so on. So this, they pass the energy back and forth among qubits. So this is the so-called time domain chevron pattern, demonstrating the exchange coupling between the qubits at the upper decoherent free frequency, which is the omega DF2 as a function of the interaction time and qubit detuning delta. The excitation will swap maximally with a period given by this number. So it's possible to have, for this configuration, to have energy exchange and also to have these gates, and you can actually see the density matrix is the real part, imaginary part, corresponding to the ideal case. The experimental one is shown. The ideal case would be everything will be 0 beside these two big blocks, but I mean, this one here is perfect. This one here on the right. The one on the left is a bit behind, a bit slower. He's also a bit shifted, a bit, there's some leakage, but overall, the fidelity of the gate is pretty good. So the experimental stuff is described in more detail in this experiment called Waveguide Quantum Electrodynamics with Superconductor Artificial Atoms by Bharat et al. In the group of Will Oliver. Has been a very great collaboration with them. And then future experiments could be looking at the following, no? To do a protected 1D spin chain. So the intuition from two atoms could be generalized to many because the interactions are pairwise. And there could be also space for readout and control lines for each qubit. So there will be on top and on the bottom, there could be these readouts. And so this is the waveguide in black. The qubits are coupled to the waveguide at multiple points here. The sign and the amplitude of each nearest neighbor coupling can be designed separately. And we have analytical expressions for this. And some results for this also in theoretical. This is a sketch of a setup with 3 giant atoms realizing all-to-all coupling. This could be generalized to more, but this is like a simpler case where A is the layout of the connection points, B is the effective system, which is one here, like 3 two-level atoms talking to each other, and C is a possible implementation with superconducting circuits. So the summary of this part is the following, that we have a giant atom coupled to waveguide multiple points, and multiple point interference effects. You can design frequency-dependent relaxation rates, and if you braid them, you can still have them talking to each other, but they're not decaying. The individual decay rates are 0, and the collective decay is also 0. Now let's briefly talk about chiral bound states. We propose tunable chiral bound states in a system composable of the giant atom with in a photonic crystal waveguide. There is no analog in other quantum setups. The chiral bound states arise due to the interference of the non-local coupling of the giant atom to multiple points in the waveguide. The chirality can be tuned, can be controlled by changing either the atom wavelength coupling or the external bias of the photonic crystal waveguide. So the chiral bound states can induce directional dipole-dipole interactions between multiple giant atoms coupling to the same waveguide. This can be implemented experimentally, and it could be used as a tunable toolbox to realize topological phase transitions. So therefore, you have this waveguide impedance, which is varying periodically in space, enabling bound states and also creating the opportunity to break translational symmetry. You have your giant atom here with these 2 Josephson junctions coupled to the right and to the left, but the right and the left are not identical. There's an asymmetry. The impedance is not the same. The impedance is asymmetric, allowing here like a round right bound state, which is smaller than the left bound state, which is bigger in this case, given the impedance potential here. So therefore, you can fix one coupling point at, let's say, x minus equals 0. You can tune the position of the other coupling point, allowing us to reach a good chirality in both directions, even perfect. A small atom cannot achieve perfect chirality. A giant atom can do so. We just try with a small atom, there's no way to do it. The chiral bound states can interact with each other. The overlap between the states determine the strength of a protected exchange interaction between the atoms, just like for normal atoms. So therefore, these atoms A and B are talking to each other, but they're talking to each other in an asymmetric way because here the coupling is stronger, this one is weaker, and so on. So the system becomes like bipartite. The coupling directions can be switched by changing the waveguide modulation. So we have here the giant atom coupled just there is some chirality bound state around the small atom, and then and this can be used to model the so-called Schrieffer-Heeger model, which was proposed initially to describe 1D polymers that conduct, like polyacetylene. So therefore, in this system, it was initially proposed to see fractional charge, dimerized phases, and then it played an important role in condensed matter physics in the 1980s and 90s, and has been a revival of interest in the Schrieffer-Heeger model because it has topological properties. And Sue was a graduate student of Schrieffer also interacting with Heger at the University of Pennsylvania, came to the University of Illinois, where I had the pleasure of meeting him. And then eventually I met all three of them. Essentially, Schrieffer was the postdoc, one of my postdoctoral supervisors when I was a postdoc, and Heger had done very important work in physics. So this is a very, very interesting model done by three great scientists here, which is very topical now in topological physics. So therefore, the summary and outlook is the following here. So these multiple couple points allow interference effects, which allow you to design frequency-dependent relaxation rates for single atoms. Two braid atoms can completely decouple the entire Hilbert space, not just a single dark state from the waveguide, but still have a strong exchange interaction. This is not possible with small atoms. The decoherence-free interaction survives if the coupling to the waveguide is chiral, has a chirality, has a like handness. Chiral comes from a Greek word indicating the hand. So there is a chirality is different from the right hand than the left hand. So therefore, the giant atoms coupled to the waveguide with a band structure with this impedance, which is modulated up and down, can have bound state that have a chirality, it could be either left-handed or could be right-handed. And then we're looking at other phenomena that can change when making the atoms giant. And before I forget here, this is something that I forgot to, essentially the superconducting giant atom interact with the squid and this coplanar waveguide at 2 points, X plus and X minus. And then this tells you the interaction between the qubit and the photons. So in this case, the qubit decays, emits a photon, and the coupling is over here, or the photon is absorbed and excites the atom. And this is the coupling here. So the interaction strength with mode K are contributed by two coupling points, which is the interaction strength has the interaction strength due to the coupling X minus and the coupling X plus. And it's possible to have the G plus minus in terms of capacitances, in terms of the frequencies being involved. So therefore, from the circuit, you can actually estimate the coupling G plus minus, and when you add them up in this Fourier transform with actual coordinates for X minus X plus, you can get the effective coupling G, which is used to describe the interaction between the light and matter. So light is absorbed, matter is excited, or matter decays and light is emitted. And this is the interaction between them. The bound state is derived from this equation here because it's a bound state involving a combination of the ground state and a photon, or the photon is absorbed and the atom is excited and there is no photon left in the cavity. So you can think of this as a system, as a state which is rotating in some sort of block sphere or block plane here. The photonic part is the real, in the real space is given by this expression here. And then it is possible, so different from small atom, each coupling point in the giant atoms produces a local photonic bound state. So those spatially separated sub-bound states interfere with each other due to phase interference. So for two coupling points at high and low impedance position, the phase relation is asymmetric along the wavelength, the waveguide, and satisfies those conditions. So therefore, you can have on the right-hand side destructive interference, and the bound state vanishes. On the left-hand side, interference is constructive, and the bound state is significantly enhanced. So therefore, the asymmetric interference relation results in chiral bound state. This is for small atom at a point X minus, a small atom in a point X plus. You put the giant atoms coupled at 2 points, you can actually suppress the contribution on the left, and you can enhance the contribution on the right, and the relative phase goes from 0 to pi. So therefore, you're creating essentially an uneven distribution of the wave function on the waveguide. You can actually indicate which parts of the waveguide get populated with constructive interference and which parts they get destructive interference. The interference between two sub-bound states is similar to the double slit experiment, where the spatial separation also leads to certain interference patterns on a screen. You can define interference visibility for the bound state at that expression there. And then this is the bound state. W0 means totally vanishes, or W2 is maximally enhanced due to interference. And this is done by changing the separation distance between the two coupling points. So therefore, this measure W that has a contribution from, let's say, one side of this sub-bound state is normalized by contributions on the right side and on the left side. And as a function of the spatial distance X plus X minus, it oscillates between 0 and 2, 0 and 2. So you can get for a W equal 2 when the distances is an integer times the wavelength, and in even one, and W0 when there is an odd integer multiplying lambda m. So therefore, the interference between these two sub-bound states, you can think of it like a double slit interference. So you're doing like a basic quantum mechanics experiments, but you can actually control it on the chip. This chiral bound state can be phenomenologically interpreted as a result of interference. So the chiral factor can be obtained via quantitative analysis. In small atom, the coupling strength is momentum independent. For giant atom, the coupling with the waveguide strongly depends on the momentum k. And you can approximate it like this. There is like a g of k goes like this. So the bound state is derived by this expression here, where there is like a decay on the left exponentially. Oh no, on one side decay is very fast, and the case is much larger. The phase difference essentially is 0 to pi. And this is giant atom coupling areas right here. The bound state is dominant on one side and is suppressed on the other side. And the coupling changes with k. This is the real part and the imaginary part. Imaginary part is here is flat, and the real part grows as a function of k. So therefore, this ends the talk. So I thank you for your attention.
Thank you, Professor Nori, for a fantastic talk. And now the session is open for the audience. For any question?
Yeah, I would like to ask one question, Satyavat.
Yeah, sure. Please go ahead.
Professor Nori, these acoustic waves, they are like the second sound of superconductivity, or they are like ordinary acoustic waves?
Oh, would you mind repeating the question slowly, because the sound is not talking about sound. The classical sound is not reaching here. So if you could speak slowly to see if I could catch again. Sorry about this.
No, I'm asking, is the acoustic wave the second sound of superconductors, or sorry, superfluid? acoustic wave, is it like normal sound wave, or is it the second sound?
Okay, so let's go back to the sound part. So the sound here is called like surface acoustic waves. Namely, it's like when you look at a lake. In a lake, there are these surface waves. Some people call them Rayleigh waves. So they are not bulk waves. They're like on the surface. And then they are used because the frequency of these surface acoustic waves can match the frequency of the qubit. Can be a bit lower, can be a bit higher, but it can match it. But then this requires a coupling between the atom motion and the electric field, because the surface acoustic wave is like this water wave moving on top of the solid. But once it gets to here, if I'm the qubit, how am I going to hear that sound? So therefore, the oscillations on surface acoustic waves are going to change this distance in the interdigitated capacitors. Because the capacitors here, as you can see, they're very extended and they get closer, far away, closer. So therefore, it is transducing the sound wave into an electrical signal that can be fed into the qubit. So therefore, the same way that I need transducers via my microphone and my headphones to communicate with you located in different parts of the world, the qubit needs its own set of microphones. So therefore, the interdigitated transducer is the headphone, is acting like a microphone and like a headphone. And this requires a beautiful balance between the qubit, which is superconducting, is talking electrically via this electric field, and the electric field is talking to the substrate via the surface acoustic waves, which is talking to the other one, which is like the detector, which can act as a source also. So the whole thing as a speaker. So therefore, this opens new avenues, because people are used to say, aha, you want to excite the qubit, I need to put microwaves. Not necessarily. You could do it via, indeed, what they did is when they sent the second sound wave, it was not absorbed because it was excited. So you need to wait T1, and after T1, pop decays, and then the second sound quantum can come. But what's exciting about this is that the whole field of quantum electrodynamics can be redone in the future, theoretically and experimentally, using sound waves. This is absolutely stunning. So therefore, we have qubits that can listen and see, but they cannot touch yet. But if you couple this qubit with chat, GPT, perhaps you could be able to actually talk to the qubit, because they can see you, they can listen to you. Probably you can have a conversation with the qubit that qubit, why the fidelity is not high enough? And the qubit will tell you, well, what is the problem? So this is, I think, is an exciting new direction for people who are looking about what to look in the future as far as basic science. Because the cavity QED has been studied for a long time, and ultrastrong coupling is an exciting direction that has been studied for the past few years. But to add sound is truly remarkable. This is, and it has not been studied so much. I mean, it's growing, but it's still in the initial stages. So there are many open questions for, at least for younger people looking for new directions. Experimentally, for instance, how do you couple many qubits to each other via light and via sound, and how will they be mixing them together? The possibilities are endless.
Yeah, thank you.
Professor Nori, I have a question.
I have a question. Oh, sorry.
Can I ask, sir?
Yes, Lava Kumar, please go ahead.
So, why are we always comparing with the microwave photons, like whether they are giant or the small? We are comparing the size with the wavelength of the light, right?
Okay, so in this case, the problem that Harosh, the reason why he got the Nobel Prize, I mean, he did beautiful experiment with Jean-Michel Raymond and Michel Brun and others, is that for a while people were wondering, how do we study light matter interaction, light matter coupling? The problem that the way to couple is via the dipole moment of the atom, but the dipole moment is too small, the charge is too small, the distance are too small, so people say it's not going to work. So they were polishing mirrors for a long time. So in the mirror, in the cavity, the photon is going back and forth, back and forth, back and forth, zillions of times to try to enhance the coupling, but it still was too small. So what they did is they take the atom and you elongate. So the Rydberg atom, you need to excite it to n of the order of 50 to 100, put an electric field. So the atom becomes long, like you can think of it a bit like a sausage, like a football field, like a zeppelin, but then it essentially looks like an antenna. Not quite, but I mean it's. And therefore, the coupling becomes strong. So the Nobel Prize to Harosh is that you could see, let's say, cat states, you could see the quasi-classical regime, you could see many exciting aspects of light matter interaction by elongating the atom. People say, okay, great, the atoms are large, but they are not really large. They're small compared to the microwaves. So therefore, if you look at this table here, you see that the ratio is very small, even for Rydberg atom, they're large compared to atom. You need to compare them with what you're interacting with. Microwaves are about 1 centimeter wavelength. They're huge. Superconducting qubits can be large, but then if you allow it even longer, you can explore new regimes, new aspects of physics that could be impossible to see before. This giant atom is a bit like there are some gods in India. I know the Shiva or some other god has many arms. So imagine this is the atom has many arms touching the environment in different places, and then the possibilities become endless because then you can play with interference effects. You can enhance some effects, suppress some effects. You have more knobs to play with. You can not only design your atom, but you can design how the atom is going to talk to the environment. This is the ultimate level of controlling quantum mechanics. Design your atom and design how your atom is going to talk to the environment. So this opens many opportunities for new science, but also future applications that we can even imagine now.
So if I'm coupling this giant atom, suppose to a so larger wavelength, like instead of the microwave, say, so then they won't be coupling to coupling at multiple points, right? Since it is microwave photons, they are interacting, so that we are saying.
Okay, depends. If you want to interact with sound waves, you need to have the interdigitated system. Now, this is more like the acoustic part. The second part of the talk was more on these multiple couplings here. So therefore, here the goal is to do the following: is to be able to get atom A and atom B talking to each other by suppressing the individual decays and suppressing the collective decays. And then in order to do that, we had to look at many different possibilities. By looking at all these possibilities, the only one that seemed to be promising to do I-swap gates, C-node gates, and all kinds of gates was the braided arrangement, because the braided arrangement will allow us to bring essentially the individual relaxation to 0 for atom A, because this is the decay, and atom B. But also we want to have the collective relaxation to 0. And the only configuration that will do it was essentially, with essentially exhaustive study. That was Anton actually was the driving force for this. And it just, the data was very clear that if you want to suppress the undesirable effects of individual relaxation and collective relaxation and enhance the positive effects of coupling, which is what you want to keep, then there is a beautiful sweet spot. With some range, you can have error bars of the order of 5, 10%, it still works. It's not like a magic point. There is some range where it works. Then it was like where things were working beautifully, theoretically, analytically, numerically, but then also experimentally. So the goal here was more utilitarian, how to get qubits to talk to each other without losing coherence. And this is very, very exciting, like because of people, they couldn't do this before with the traditional approaches.
Thanks.
Professor Nori, can I ask a question?
Yeah.
So real atoms, when they are excited, so they have a natural lifetime after which they decay back to the ground state. So what about these giant atoms? Do they have a natural lifetime, or that lifetime can be tuned some way?
Yes, okay, it can be tuned up to a certain limit, essentially not infinite. Like in this case, for instance, like so this is the qubit. So you excite the atom and you wait a certain period of time. So you excite, let's say, qubit A. So forget about B. B is decoupled. You need to do it for A first, you do it for B. So if you focus only on A, you excite it, and then you wait. And then depending on where you're exciting a different frequency, you can see a decay of 3 microns. So therefore, after 3 microns on average, pop, you're in ground state. But then you can tune the frequency here, it could be frequency, and then you wait 11 microns, and you can get up to a point where you can get 32 microns, which is not too bad, at least for this qubit here. So therefore, you can actually tune them, but then you need to tune them separately for A and for B. And you want to do it because the qubit decouples from the waveguide at a decoherence-free frequency, which is equal to 4.6 for this particular qubit, with a lifetime of about 31, 32 microns. I mean, of course, if you do more careful, substrate, all the stuff could become longer. But then you need to do the same for the other qubit separately, which is qubit B. And then if you do it, so in this case, if you want to change the decay, you have control over the phase, because the phase is controlled by the delta X. I mean, the delta X is fixed, but you can do another experiment with a different delta X and a different delta X. And then this affects the decay rate here. And you do it again for B. And after you do it for B and for A, then you have the following. Exactly, you can do it for A, 4.6 something, and then here you get 4.5 and 5.2 for this one here. And then you could try to find a place where you can actually suppress the collective decay. So there are some knobs you can play with here to be able to bring this to individual decay 0, and collective decay 0 also.
See, what I was interested in is that since this lifetime can be tuned, after how much time they will decay to the ground state, can this be used to sort of monitor this decoherence-induced wave function collapse? So how does a wave function collapse over time? So can this be monitored?
Yeah, this is monitored because in this case here, you excite the system and you wait a certain period of time, but of course you need to do many experiments. And this 3.1 microseconds or 31 or 32, these are averages. So you need to do it many times. And then like in every decade, atoms, superquantum qubits, ion traps, it can be longer, it can be shorter, but this is like an average. The T2, it tells you the average time the energy levels are not fluctuating, because when the energy levels fluctuate, you're messing up T2. So you could have a very long T1, but if the energy level difference fluctuates, then T2 is suppressed. So you want to have T2 fixed, but also you want to have the T1. The T1 can be extended by doing something called the quantum Zeno effect. Namely, you can do multiple some people do that essentially before T1, for instance, if you wait 30, or even like 25 or microsecond, you do another measurement. So you're projecting, if you're talking about wave function color, to the excited state, and you do it over and over again. Then you can extend T1 via quantum zeno. So therefore, yes, you can use projective measurements to extend T1, and some groups do it.
Okay.
It's not going to help you on T2, as
Mhm.
far as I know, but it will definitely extend your T1 up to a certain point, because of course there is a limit of you can do this. And
Okay. Thank you.
Since the same waveguide is exciting both the qubits, we should be careful that the two qubits have different excitation frequencies that they're detuned, unless while we are trying to excite qubit A, the qubit B could also get excited.
yes, you're raising a good point. Yes, yes. Yeah, I agree. I agree, sir.
Yeah, thank you.
Is there any more question?
Is this decoherence-free thing we can see in the when the both the qubits are coupled to the same waveguide? Is
Yes.
it like the correlated emission lasers? We see that the spontaneous emission between different levels, they get a destructive interference between them. Due to that, they can reduce the spontaneous emission.
No, this is different than lasing. I don't see the
In that
relation.
multiple levels also, if there is a destructive interference between the transitions,
So you're saying that there is an analogy between this
spontaneous emission between different levels. If
yeah,
there is a destructive interference.
yeah, perhaps there are some analogies, yes, but I see them somewhat different, because here the goal is to be able to, for instance, to achieve a gate, could be I swap or square root of I swap, with a high fidelity, and then because you can first identify the two frequencies at which the qubits are protected for relaxation, and this enables turning the protected interaction on and off by detuning the qubits. So in this case, for instance, you can do a pi pulse on qubit B, and then detune qubit A, which was here. You detune them and you put them interacting with qubit B for a certain period of time. Then you pull out. So therefore, and you read out the signal. So therefore, the readout signal, it tells you that the excitation jumps from qubit A to qubit B, and qubit A to qubit B essentially is oscillating back and forth. And then it does it, of course, there is some decoherence. I mean, it doesn't go on forever, but it goes for a fair amount of time. And this, for being the first experiment on this, was pretty good. So the trick here is to identify the two frequencies at which there could be a protected relaxation, the first one, then the other one, then afterwards to tune the system in a way to achieve this decoherence-free coupling. And then at that point, you need to essentially excite one. And after, essentially, they're both in the ground, so they're both asleep. So you need to first wake up one, then interact them. And then when they interact, and then they begin the excitation that you already pump into the system is going back and forth between them. So is there might be analogies to laser, but I see this more like a Rabi oscillation, where the system is absorbing energy, then emitting, and then sending it back to the other one. And it's like it's a bit like swapping energy back and forth between one qubit and the other one. Ideally, you would like this decay to be essentially zero. You would like this to go on forever, which, I mean, it's not going to happen, but at least like you want to delay it as much as possible. So.
Doesn't this both the qubits like get into a state like decay state, whether they are symmetrically or anti-symmetrically coupled? So one state, I mean, when they are symmetrically coupled, they do make a collective emission, right?
Correct. Huh? Mhm.
So
So you're trying to do an analogy between, let's say, symmetrically coupled, anti-symmetrically coupled, symmetrically coupled, symmetrically coupled.
yeah,
This is an analogy, which is an interesting analogy, but what we see here, we couldn't figure out a way to achieve this using the normal atoms. I think for this, we needed the multiple connection points, and we needed the ability to have these multiple connection points to be able to play with these interference effects here. There are some partial analogies with normal atom where you can get individual decays to zero or collective decay to zero, but to do individual decays and collective decays, both of them to zero, that we couldn't do it with the normal atoms. But I'm sure there are analogies with many different phenomena. Like
okay, thanks.
So we are stopping here, asking any question because we are running a little bit late. We'll go to the next talk. Thank you, Professor Nori, for the nice
thank you.
talk. Yeah.
Thank you for the invitation, and thank you all of you for attending this. Okay.
Thank you, Professor Nori. Thank you very, very much. Very wonderful talk.
Yeah. Okay, great. Thank you very much. I appreciate the invitation. So let me just turn off the here.
Screen sharing.
Yes, the screen.